Hello, my dear students, and welcome again to a new chapter with this REN 616 Grid Connected PV System course. If you remember our previous two chapters where we first considered the semiconductor principles related to solar cells, or what's called a photovoltaic, till we reach what's called a solar or a PN junction working as a solar cell. Then in chapter 2, we have jumped to what's called the cell level. So we studied together the construction of a complete cell with different topologies and different layers, considering what's called the encapsulation, front contacts, the metal back contacts, the reflection on the surface, and other technologies related to solar cells as the thin film technology, the electrochemical technology, and the flexible solar cells or organic solar cells technology. Now, let's jump now one step further in our bottom-top approach. Today, we will consider what's called a PV panel or a solar cell or a solar module. And today I will use a different way of demonstration rather than using a PowerPoint slides. I will go through a typical data sheet for a solar panel so that we can understand together the different parameters, what we can call a macroscopic parameters describing a solar panel. If you remember in the second part of chapter 2, we have studied together the IV characteristic curves for a solar cell. And we understand some major parameters like the open circuit voltage, the short circuit current, the maximum power point, the current at which the power is maximum, or what's called IMP, and the voltage at which the power is maximum, the field factor concepts, and all these stuff. But these were somehow focused on at cell level. Now we are going to demonstrate this on a module level. So in this case, as I mentioned, we have a typical solar cell or a solar module data sheet, and we are going to describe step by step these parameters. So let me go directly to the second page where we have this specification, and let's start together following this specification item by item. Of course, as a first row, we discussed, or the data sheet demonstrate the manufacturer. I mean the manufacturer name, the model name, which is, of course, not for our interest. And then let's go to the third row. I think you already can see my mouse here. So the third row is what's called the cell type. And here, I think we focused on this before when we consider these three famous types of silicon, considering monocrystalline, polycrystalline, and amorphous. And as you can see here, the material used for our panel now is a monocrystallized silicon. And beside that, you will find two dimensions, which is 78 millimeters times 156 millimeter. This typically demonstrates the area per cell. Again, this is the area per cell, not the module area. Then the second row, which is, or the fourth row typically, which is the number of cells. Here, this module contains 120 cells. This module contains 120 cells connected together. Then the maximum power rating, or the Pmax, is 260 watts. Now, this is what is the 260 watt? Let me jump directly to this PV curves, if you remember. So this 260 watt, you can see that the power axis is the axis to the right, this one, and here at 100 watt per meter square radians, this is the top curve, this is the IV curve, and the corresponding PV curve is this top blue one. So this point is 260 watt. What is this 260 watt? This is the maximum power at what we call the standard test condition. So if you have an intensity of a sun of 100 watt per meter square, and you are working at the maximum point, then your output power will be 260 watts. This is the output power. Okay. Then we have warranted minimum power max, which is still 260 watts. And this is a test condition rating. Another test condition, this is somehow out of the scope of our case. This is a US test condition called PTC. It is not generally used in Egypt. Then we have some basic parameters related to the open circuit voltage, which is 38 volts, the short circuit current, which is 8.98 ampere, the maximum power voltage. Again, I think you are now understand the difference between the VOC and VMP. The VOC is the open circuit voltage. However, the VMP is the voltage at which the power is maximum, which is 31.4 voltage. If you remember, my dear students, I told you usually that this value is around 0.8 of the V open circuit. And you can find it here. This 0.8, I think we are now subtracting 20%, which is 3.8 times 2. It's around 7.8. So if you subtract 7.8 minus 31, you will get 31.2, and this is 31.4. So it's 0.8 something. So this is typical, or this is empirical formula you can use when you multiply the open circuit by about 0.8, you can get this VMP. And again, this is IMP and this is I short circuit. And also, if you remember, my dear students, that usually this IMP is around 0.9 something of the I short circuit. Again, you can find this here. So this is simply, my dear students, the case where you have the VMP and the IMP, which represents the point at which the power is maximum. Then we have the efficiency, and the efficiency is simply the 15.7% efficiency, which is typically a usual number whenever you are considering solar cells. However, as I mentioned, maybe nowadays, if you go to find a well-fabricated solar cell monocrystalline, you can reach 20 something, you can reach 21 or 22%. But commercially, the most famous solar cell, the most famous solar modules are in the range of 17 to 19%, which most of these Chinese fabricated solar modules or something like that. Okay, then we have what's called an aperture efficiency. This aperture efficiency actually is not generally used, but let me try to demonstrate the difference between the efficiency and the aperture efficiency. If you remember the equation of the efficiency, I will try to use a pen somehow. So okay, yeah. If you remember the equation of the efficiency is power input over the power output. And in the output power, if you remember, sorry, in the input power, if you remember, which is in the denominator, we simply multiply the one sun, which is 100 or 1,000, sorry, thousands watt per meter square. We multiply this by the area, which is very normal, because as you know, this is a power density. This one sun condition, this 1,000 watt per meter square is a density of power. So you have to convert it into power, so you can divide power over power, because in the input you have the power input, which is simply V open circuit times ion short circuit times the V factor, if you remember. So in this case, you multiply times the area. So what is your area? Simply, your area is the area of your module. So simply, you have a module here, which has a length times width. So this is typically the area. So you get some sort of efficiency, which is a 15.7%, for example, in this case. However, if you are considering what we call the aperture area or the effective area. What is the effective area? Simply, it's something like that. If you remember, we consider that this module contains 120 cells. So I would assume that we have cells like that. And so on here. And also we have some cells here, and so on. Then we have something here. So these are the cells, somehow arranged in rows and columns. Of course, there is some area which is between each cell and its neighbors. So if you consider the area of your module as typically the total area, then we consider that this is the efficiency. However, some people comes and say, no, this is not true because this is not the effective area. The effective area is typically 120 times the area of each cell. That's true. It's 120 times the area of each cell, which is, of course, will come with a number smaller than this A, because there is some areas which are not considered as a solar cells in the module. So this will result with a smaller area. So typically, if you use a smaller area here, you will get a higher effective efficiency, or what we can call aperture efficiency. That's why if you return here to this, you will find that we have two efficiencies. The first is this 15.7, which is most likely used. And the second, which is 17%, which is slightly higher because you reduce the effective area. But this is not so commonly used in industry. However, this you can consider as an efficiency as well. The tolerance is between plus minus 5%. And we have a static load test paused with 5.4 Pascal for the pressure. Number of bus bars per cell is 4 bus bars. This bus bars is simply these bus bars of copper that's connecting cells together. So usually when you have a module, you find cells are arranged in rows and columns, and there is some copper wires connecting, or copper bars connecting this together. This is okay. We find number one, normal operating cell temperature. This is very, very, very important problem. This 45.7 very important. What's called the NOCT, or the normal operating cell temperature. Usually, my dear students, when we consider a temperature in a solar cell, we consider the temperature of the solar cell, not the temperature of the environment of the solar cell. And this is very misleading. So if you are working at a normal ambient temperature, for example, 30 degrees, your solar cell surface, top surface, I mean, will have a temperature of about 45.7 degrees Celsius. And this is very normal. This is not a high temperature. Those people who did not understand this well, they got confused when they measured the temperature. They thought that it's a very high temperature. Normally, when we consider this STC condition, or standard test condition, we consider this standard test condition at an ambient temperature of about 27 or 30 or 25 or something like that. But please don't forget, in lecture 1, when we consider this, what's called a hot photon absorption. If you remember, my dear students, when we consider together the process of absorbing photons with energy greater than energy gap, and we consider that any energy, any excess energy greater than this Ag will be converted into kinetic energy that will convert later on into collisions and into temperature. That's why typically a solar cell normal operating cell temperature is 10 to 20 degrees higher than the environmental temperature. So, for example, if the temperature today in Cairo is 25 degrees Celsius, and you use an infrared camera, for example, to capture the temperature of your solar cell front contact, usually you will find this temperature is between 35 to 45 degrees Celsius, which is 10 to 20 degrees higher than the environmental temperature. And again, this is very normal. This is not high. As you can see in the data sheet, the working temperature is 45.7 degrees Celsius. And now when we consider this 260 watt, this 260 watt were measured under, or was measured, sorry, under this for 45.7 degrees Celsius. So this is the normal. It's that's why we call it a normal operating cell temperature. If the ambient, if for example we go to the high Egypt, for example, far into Aswan, or into maybe deeper, going into Sudan, or in a very hot area where the temperature is normally 45 degrees Celsius, then in this case you will find your operating cell temperature of your solar cell reaching 65, 70 degrees, because again it's 10 to 20 degrees higher than your operating temperature or your environmental temperature. And in this case, we will consider the effective temperature. This will be considered in this lecture after a few minutes from now. So that's why this is a very important point. Then we have the maximum system voltage. This is related to when you connect series and series and parallel modules. Maybe we will consider this in the next lecture when we start going into system level. A fuse ratings. This is the fuse used dimensions here. As you can see, this is the dimension of the module, and you can easily distinguish now between this number and between this number. This is the area for one cell. So to calculate the aperture area, what you are going to do is to multiply 120, which is the number of cells, times this area. But now this is the area of the module. This is the overall area of a module. So as you can see. Okay. Then we have the weight, number of modules per pallet. This is when you are going to buy a huge number of modules for exportation, something like that. We have that. This is the type of the terminal, fire rating, and all these industrial aspects. So I think we cover now some important parameters considering one module, but we are still having two very important environmental effects that we should consider while considering this this module. Maybe we have not only two environmental, we have a lot of environmental effects, but I will first start with the most important. But generally, we have to agree that the operating of solar cells is highly influenced by environmental conditions. All these good numbers listed in this table, like this 260 watts, this 8.2 ampere or 31.4 voltage, all these parameters are listed considering what we can call a standardized condition. But unfortunately, nothing is standard in life. Whenever you go to operate your solar cell into a normal operation, you will not find these in standardized conditions. Unfortunately, what you will find is what we can call harsh conditions or not standard conditions. But what type of conditions we are looking for? Mainly, there are 4 or 5, let me say 5 major environmental conditions we are considering. 2 of them are critically measured and highly studied, and 3, let's say, comes in the second degree of importance. The most 2 important environmental conditions are the irradiance level and the temperature. the irradiance level is simply the amount of power density reaching the Earth at a certain location and a certain time coming from the sun. And of course, temperature. As a second level of importance comes dust accumulation, and this related to the nature of the position you are locating your solar cell. So if it's going to be located in a desert area, dust accumulations play a very important role. Wind speed and humidity. And of course, also humidity is another parameter function in the location. So whenever you are going to implement solar cells on an side by a sea, for example, or a river or something like that, or in any place on the earth where there is a relatively high humidity, you should consider. However, for example, whenever you are implementing solar cells in Cairo, for example, humidity is not a big factor. Maybe dust accumulations is more important. So these 5 parameters, 2 of them are very major everywhere, irradiance level and temperature, and 3 of them may fluctuate from one position to another, depend on your selected location for a solar cell. So let me first start in this part of a lecture to consider what's called the effect of irradiance and the effect of temperature. And still, I'm going to use this data sheet. Maybe when I go to the second or the second part, which is the dust accumulation, the dust accumulations, wind speed, and also the temperature. Dust accumulation, wind speed, and humidity. Maybe I will consider another aspects. Okay, let's start with the irradiance level. This is a very famous relation considering irradiance and IV curve. Of course, this have somehow a theoretical background beyond. So if you go to this IV curve, IV characteristic equation, we already see in the previous chapter, when we consider, if you remember, when we consider this one diode model and this 2 diode model and so on, you can have a further mathematical derivations in order to study deeply the effect of radiance on the IV curve. But maybe this is more toward those who are considering the electronic perspective of a solar cell. But for a system level engineers, which may be the main bias of this course, we are going to use empirical understanding to study or to understand this curve. If you remember, my dear students, coming from the first lecture, that the generation of each electron hole pair in a p-n junction is related to the absorption of photon. So each photon collected will generate an electron hole pair, which will then move in the drift of a p-n junction to create a current. And from this perspective, you can easily understand that the current is directly proportional to the irradiance. The higher the irradiance is simply mean that you are or you have more photons reaching your solar cell. And knowing that each photon will convert into an electron, and current is the rate of a change of electrons. So the higher the number of electrons, the higher the current. So simply you can understand that the higher the number of photons, the higher the current. Or the higher the intensity, the higher the current. And this is typically seen here as there is a linear proportionality between the irradiance and the curve. And from this perspective, my dear students, you can use solar cells as a very accurate sensor to sense irradiance. So, for example, if you make a short circuit test for your solar cell and you find that your current is around 8.9 ampere, gain, which is the short circuit current, then you can assume that at this time of the day, the irradiance is around 100, or sorry, 1000 watt per meter square. And typically, if this current drops to be 4 point something ampere, then that means that your radius is half sun or 500 watt per meter square, and so on. So this number, which is the short circuit current, which is easily measured in any solar cell using just a multimeter, can be a very good indication to the level of irradiance of the solar cell or this place. I mean. So you can easily find these parameters here, considering the different radiance level. The higher the radiance, the higher the current, up to what we call the one sun condition, which represents the typical standard condition for a solar cell. As I previously mentioned, whenever you go into a real measurements, your sun intensity may exceed this 1000 watt per meter square. This is very normal. The 1000 watt per meter square is the average maximum, is not the maximum. So in Egypt, for example, when you go do some measurements in midday in June or July, or maybe in August as well, you will find irradiance reaching 100, 1100, 1200, and this and so on. So in this case, you could expect higher current than usual. And this, by the way, this high intensity, I will consider it somehow in a few seconds, but let's focus here. So this is very normal. And accordingly, the higher the IV curve, the higher the PV curve. And this is, again, very important. But there is also some technology, it's not a new technology, it's somehow relatively old technology related to solar cells, when we consider what's called solar cells under concentrators. Let me use on my whiteboard again here. So now, generally speaking, you have your solar cell somehow adjusted like that, and you have your sun rays coming in this direction. Maybe in one lecture or two lectures from now, we will consider this adjustment in the solar cell angle related to the position of the sun and so all these stuff. But in some applications, we use what's called concentrators. This concave and convex matters that reflects sunlight or sunbeams and turning them again into a solar cell. In this case, what you are doing is you are focusing more intensity, more light, more photons to your solar cell. And knowing or applying the concept that the higher the number of photons, the higher the current. In this case, you should expect output from your solar cell greater than the standard condition, because typically you are sending to your solar cells photons greater than what is in the standard condition, which is this 1000 watt per meter square. However, and based on the physical understanding that in life there is nothing as a infinite increasing function, when you are going to plot the efficiency of your solar cell again is the intensity. This is the intensity, and here let's put the efficiency. You will find a curve like that. And this point is very famous in solar cells. This is around 2.7 sun. A 2.7 sun, which is typically 2700 watt per meter square. What's happened? The higher the intensity, the higher the efficiency. So whenever you increase your intensity greater than 1000 watt per meter square, you should typically expect higher and higher efficiency. Till you reach a point here, it's better here not to make it against efficiency, I think. Let me use an eraser. I'm sorry. Eraser, yes. Yes. I think it's better here to make it in terms of power, extracted power. So the higher the intensity, because the efficiency is constant, what is increasing is the power, not the efficiency. The higher the intensity, the higher the power you are collecting from your solar cell. Till we reach what's called 2.7 sun or 2700 sun. At this point, your power will decrease. This is very interesting phenomenon because typically you are increasing the light as you go here, as you go toward the right direction, you are increasing light, but your extracted power is decreasing. Why? Because at this point, another important parameter starts to dominate, which reflects on the power extracted. This dominating parameter is the temperature. Because simply, my dear student, when you direct your solar cell into a higher intensity of light, that means that your solar cell will become higher and higher in terms of temperature. Again, by extracting each photon, this photon generate an electron, that's true, but don't forget that the extra energy greater than Eg turns to a temperature or a thermal energy. So when you increase the number of photons reaching the solar cell, of course you increase the number of electrons, but you also increase the temperature. And herein, another very important parameter become to dominate, which is temperature. So back to the slides, or back to the herein the temperature effect. This is a very, very important graph related to each solar cell, describing a very important three parameters, what's called alpha, beta, and gamma. The alpha, beta, and gamma are the three parameters describing the variation of the solar cell parameter with temperature. As I mentioned with solar cell radius, we can reach this phenomena, or we can study this phenomena mathematically, referring back to the IV characteristics equation. However, to make life easy for you, we are going just to demonstrate this in a conceptual way. So, as you can see, alpha, the first parameter, is a positive parameter, which means that the higher the temperature, the higher the current, because this alpha describes the rate of a change of current per each degree Celsius. So when you increase your temperature by 1 degree Celsius, your current will increase by 0.056%. So if it's 10, it will become 10.0056 ampere. If it's 100, it will become 100.056 ampere, and so on. However, for both voltage and power, your voltage decrease, because now the coefficient is negative. Your voltage decrease with each higher or each increase degree Celsius of temperature. And by comparing these two numbers, my dear student, I'm sorry, by comparing these two numbers together, you can easily observe the difference. With current, you are increasing 0.05% per degree Celsius. But with voltage, you are decreasing 0.35% per degree Celsius. It's roughly
7 times the percentage, 0.05 to 0.35. That's why the overall increase, the overall performance of a solar cell with respect to temperature is in negative. This is observed with this gamma coefficient, which represent the variation of the power extracted per each degree Celsius increase in temperature. And that reflects what's happened at this 2.7 sun, at this 2,700 watt per meter square. In this point, the effect of the solar concentrators turn against your application because temperature effect dominates and your power starts to decrease more and more. So this is a very important effect, and it is extremely and significantly important to consider the effect of temperature when you are designing your solar cell in what we can call a harsh conditions with respect to temperature, because your solar cell will be degraded or you'll have a reduction in your power, which with each degree Celsius increase. Let's make a very simple calculation. If we assume that our normal operating cell temperature is this 40, what's here? Yes, 45.7 degrees Celsius. And let's assume by a way or another, we locate a solar cell in a place where the overall environmental temperature is high, which leads that your operating cell temperature for your solar cell will increase 10 degrees above normal. So this 45 becomes, for example, 55. That means that you are now 10 degrees higher than the normal operating cell temperature of the NOCT. Accordingly, what will happen here that your overall power will be reduced by 4.5%. Believe me, this 4.5% is a very big amount, because your sizing, which we will learn later on in the next lectures, is mainly depend on making a matching between your power generation and your power supply and your power demand or your load. So if you have a 4.5% reduction, which is nearly 5% reduction, this destroys the overall process of the sizing process. And accordingly, you have to take care of this effect to oversize your system to avoid any degradation or reduction related to temperature. That's why considering temperature is a very critical parameter in solar cell. And this curve actually represents also the variation here. I think this is the irradiance in watt per meter square, and this is the power maximum. So you can see that by increasing the irradiance, this is the linear relation between the current and the radiance, which we already described here. If you remember, we described that this is a linear relation. So you can see this linearity here. And maybe I forgot to mention that theoretically, V open circuit is affected somehow with the radiance, but this effect is a logarithmic effect, which is a very, very weak effect. So most likely, when you are dealing with industrial measurements, you can assume a constant V open circuit with respect to radiance. This is not theoretically correct 100%, as you can see this yellow curve, but as you can see, the current variation is dominating linear function. That's why even when we plot the power, you can see that power is typically affected of current rather than to be affected with open circuit voltage, and this is clearly observed here. So you can somehow ignore the effect of open circuit voltage. However, for those theoreticians who are dealing with the electronics of solar cell, like myself, we have to consider these V open circuit variation, and you can visit a lot of literature where you can find a theoretical one-to-one step analytical models to describe the relation between the open circuit and temperature. And as I mentioned, it's a logarithmic relation. So this is, for me, what we can consider, and the two common, let me say, the two common environmental parameters affecting solar cells, the radiance and the temperature. In the next part of chapter 3, I will going to consider some secondly important parameters like dust accumulation, like wind speed, and also like the humidity effect. Thank you very much for your concentration, and see you later on with part 2 in chapter 3. Thank you very much.